Chapter 10 is a continuation of what we've learned previously. Remember, we ended up our discussion in Chapter 9 with Lewis structures. From here, we're going to go on to the geometry of the electron pairs, the molecule itself, and end up with a discussion of molecular polarity. So being able to draw Lewis structures is going to be essential for this chapter. The geometry of the molecule is the general shape of the molecule determined by the positions of the atoms. Are they going to take a triangular form, a square form, or any of the three-dimensional forms we discuss? So that is the shape of the molecule. We can predict the shape of the molecule using what we call the VSEPR model, a valence shell electron pair repulsion model. A lot of words in here, but it means this. Electrons are in the valence shell of atoms, either as bonding pairs or lone pairs, but they exist as pairs. They repel each other. As a result, they want to be as far as possible from each other to minimize repulsions. And in this discussion, when I say electron pair, I mean the combination of bonding pairs and lone pairs together, all of them. So when I say electron pairs from now on, it will mean the sum of bonding pairs and lone pairs. In this electron pair repulsion model, electrons are assumed to be found in domains. They're either as bonds or non-bonding pairs. But there's a catch here, there's a difference here, a unique situation, that single, double, and triple bonds all count as one domain. So even though it's a double bond, a triple bond, 2 pairs, 3 pairs shared, we're going to take it to be a one single domain. And each non-bonding pair will make one domain. So what we're interested in is in the total number of domains. For example, in carbon dioxide, there's a double bond here, counts as 1. There's another double bond here, counts as 1. And that's it, there's nothing else, so there are 2 electron domains. In ozone, the central oxygen, we're going to pay attention to the central atoms. It has a single bond, a double bond, and a lone pair, each counting as 1, so a total of 3 electron domains. In ammonia, nitrogen, the central atom, has 1, 2, 3 bonds, and 1 lone pair, making a total of 4 electron domains. This is how we count domains. Now, for valence shell electron pair repulsion theory purposes, determine the number of bonding pairs, lone pairs, and the total electron domains on the carbon and nitrogen atoms in the hydrogen cyanide molecule. Once you determine the number of domains, you can determine the shape or the arrangement that they will assume, that they will take. The number of domains is given as pairs here. So this is the number of domains. If you got 2 domains, 2 electron pairs or electron groups repelling each other, the best way to arrange them as far as possible is to put them on opposite sides with an angle of 180. And we give this arrangement a name, linear. If you got 3 electron domains, then they take the places, the corners of an equilateral triangle with an angle between them 120 degrees. And we call this arrangement trigonal planar. When you got 4 electron groups, now we need to move to 3 dimensions, because if you put 4 groups in the corners of a square in 2 dimensions, the angle between them will be 90. But if you put them in the corners of a 3-dimensional shape tetrahedron, each corner occupying the electron domain, the angle will increase from 90 to 109.5. Larger angle means bigger separation between repelling groups, so therefore lower energy. So this will be the arrangement of 4 electron domains called tetrahedral. When an atom has 5 electron domains, the shape, the arrangement of electron domains is called trigonal bipyramidal. It has this name because it looks like 2 pyramids sharing the same triangular base. These 2 or 3 positions, called the equatorial positions, because they're on the equator that cuts the shape in half, they make the corners of the equilateral triangle. The other 2 positions, called the axial positions, they are at the apexes of the pyramids, and they're called the axial positions. So there are 2 different positions in this shape: axial positions and equatorial positions, and therefore there are 2 different bond angles. Equatorial positions are separated by 120 degrees, and equatorial and axial positions are separated by 90 degrees. This is the only shape with 2 different positions. As you see in the shape with 6 electron domains, the positions are identical. We call this the octahedral arrangement, that there are 6 positions, 1, 2, 3, 4, 5, 6, that correspond to the corners of an octahedron, means 8 face. All bond angles are 90 degrees, so all positions are identical here. Here's a summary of the 5 different arrangements that we have seen so far for 2, 3, 4, 5, and 6 electron domains. The balloon models also show how these different electron domains can be placed according to their total numbers.